Hello, this is Math 280, Multivariable Calculus. I'm Professor Wheatley. Today's topic will be our last in the examination of partial derivatives. We'll talk about Lagrange multipliers. So, we talked last week about maximizing and minimizing a function. So sometimes you want to maximize or minimize a function, but you want it to be maximized or minimized on a certain curve or surface. So we want it on a curve or surface. So we saw in the last section how to calculate extreme values for various functions. Well, now we're adding the extra constraining factor that I want the maximum in the function to lie on some curve or surface. Okay? So what do we have here? We have optimization subject to a constraint. Okay? And there are various methods of solving these. One of them is Lagrange multipliers. We'll look at that. So Lagrange multipliers is one method of solving. Okay, so how does it work? It's probably easiest explained in the 2D case, but then the 3D case is simply analogous to that. You just raise a dimension up. So let's talk about the 2D case. So we've got general methodology. Okay. Okay, so you want to maximize some function of two variables, f of x, y. Okay, and you want to do it subject to a constraint, of the form g of xy equals k, right? So some function of two variables that is a constant value or a level curve of some function g, right? Okay, so you want the max value of f lying on the level curve g of xy equals k. And certainly if I wanted to minimize, it's the exact same idea. I'm just using maximize, and you can just move over to the minimum case without any change. Okay, so a picture. All right. Let's use multimedia here. So let's draw some level curves of f. Okay, so maybe there's f of xy equals 9, and f of xy equals 8, and f of xy equals 7, and so on and so forth. So here what we have is, so the pink is, or are, level curves of f, e.g. f of xy equals 7, f of xy equals 8, f of xy equals 6 maybe down there, but they're a bunch of level curves, right? And so they're all of the form f of xy equals c, okay? Well, let's put up here in blue then where our level curve of g is. So maybe our level curve of g looks something like that, right? Maybe there's a level curve of g. So maybe this is g of xy equals k, right? And maybe it hits level curve of f right there, okay? So the blue is the level curve g of xy equals k. Remember, these are different functions. F and g are not the same functions, so their level curves won't look the same, right? Okay? And so I want to maximize f subject to this level curve g. So do I want to erase? Not yet. So to maximize f subject to g of xy equals k, well, think about it. What I'm looking for is I'm looking for the level curve of f where the level curve of g intersects, right? I'm looking for the largest value of c where the level curve g intersects here, right? So I want to find the largest value of c such that g of xy equals k intersects the level curve f of xy equals c, right? And I'll write this down in a second, but to look at this geometrically, think about it. So here's a level curve g of xy equals k. Here's level curves f of xy equals c. I've only drawn a few of these up here, but between these level curves are lots more level curves, right? There's f of xy equals 8.5, and f of xy equals 8 1/3, and so on and so forth. And so if the blue actually crossed through this level curve here, f of xy equals 7, and it ended up, say, here, well, the level curve f of xy equals 7 wouldn't be the max value. Instead, it would be f of xy equals 7 1/3 or 7.5. So at some point, there is some pink curve here where the blue just touches. It doesn't cross through at more than one point. It just touches there, okay? And so let's see. So carrying on with the black here, this occurs when g of xy equals k and f of xy equals c just touch, right? They don't cross through. They just touch at a point x naught, y naught, right? And so there's our point, x naught, y naught. So there's x naught, y naught, right? Okay. All right, let's erase this and give myself some room to work here. So keep the picture in mind. In fact, maybe I'll leave the picture up here. Just erase the words. Right, so let's get rid of this stuff. Okay. So get it all out of here. Okay, so you have this point where they just touch. Where am I now? Yeah. So at x naught, y naught, the point where they just touch, the curves share a common tangent line, right? I mean, these two curves are tangent at that one point. They touch at one point, so they share a common tangent line, okay? And that means that the gradient of f at x naught, y naught is parallel to the gradient of g at x naught, y naught, since both these vectors, since both are orthogonal to the common tangent line, right? Right? So the gradient, remember, the gradient is orthogonal to a level curve at every point, right? So these two share a common tangent line here, these two level curves. Therefore, their gradients are parallel because they're both orthogonal to that tangent line, that common tangent. Okay. Well, this is the 2D case. Well, the same argument again applies in 3D. Let's get rid of this. So let's see. So the same argument applies to a function of three variables, f of x, y, z, maximized on a level surface, g of x, y, z equals k in space, right? The same exact thing applies there, right? So let's see here. The only difference is when you're on a level surface, they don't share a common tangent line, they share a common tangent plane, right? So here, the surface, the level surface g of x, y, z equals k. Where am I here? So it touches f of x, y, z at a point, x naught, y naught, z naught. So there's still a common point of intersection, right? It's still a single point of tangency, right? Let's see here, where am I? Oh, yeah. And because they share the same tangent plane, the gradients are, again, orthogonal. So an f of x, y, such as f at a point, and f of x, y, yeah, that's right, is parallel. Should be is parallel to the gradient of g at x naught, y naught, z naught, right? And so what does this all mean? Well, in either case, the gradients are parallel. That means that the gradients are, they are different only by a constant multiplier, right? So therefore, and here's the big point of the section, we seek a constant such that, well, actually, a constant lambda, it's a lambda, such that, where am I here? So the gradient of x, y, z is equal to lambda times the gradient of g, x, y, z. So the gradient of f is a constant multiplier of the gradient of g, right? And that may happen at more than one point. I mean, it could be that those level curves touch at several different points, not all of them are the max or min, but it could happen. So this could be more than, I mean, this could be several cases where this is going on here, right? And so the constant lambda is called a Lagrange multiplier. Okay? So we're looking for this constant. And the nice thing is sometimes we needn't even find it explicitly. We just need to know about how it relates these two functions together without knowing exactly what it is. Okay? All right, so how do you use this stuff? So there's the methodology behind it. Probably what we really care about is how to use it in practice, so let's do that. Okay. So to use Lagrange multipliers to solve these kinds of problems, well, first thing you do is you find all values of x, y, z, and lambda such that our earlier relationship was true, that the gradient of f is a constant multiple of the gradient of g. And again, this may happen at more than one point. You might have several points where level curves of f intersect with the level curve of g, right? And then, well, once you have all those values, you just do what you used to do for any max-min problem. You take all the possible choices for a max-min and try them in f. So you evaluate f at these points, and the biggest value is the max, and the smallest value is the min, right? So it's like we did for the other extreme value problems. You have choices for this. Check them out. Biggest one's the max, smallest one's the min. Okay, let's try one of these here. So suppose you, let's see, what do you want to do here? You want to make a rectangular box without a lid, and you want to make it out of, to be made from, let's see here, where am I? 12 square meters of cardboard. All right, so you have some constraint revolving around how much cardboard you had to make the thing, right? And you want, what do you want to find? You want to find the max volume. Find the max volume of such a box. Okay, so first things first. We want to maximize the volume of a rectangular solid. Well, that's just length times width times height, right? So this is the function to be maximized 2b. So there is volume of a rectangular solid, length times width times height. Nothing fancy going on there. Okay. What are our constraints? Well, let me draw a picture. So let's see here. Did I want to make all those? Yeah. So that's a solid line, and that's solid, and that is solid there, and I guess maybe the back of this should be dashed too, shouldn't it? There we go, right? Okay, so there is your rectangular solid there, your box, right? And so the area of the box is what we care about here. We're not looking at perimeter. This is not a single measurement. This is a square measurement here, so we want area. This is meters squared. So let's see. We'll call that side x, and we'll call that side y, and we'll call that side z. All right, so x and y make the base up. Z is the height of the box. Well, how much total area is there? Well, there are two sides made from y and z. There's the front side of the box and the back side of the box. So there's 2yz, right? Because yz is the area of this piece of cardboard. It's the area of that piece in the back, too. There are two sides, the left and right side of the box, that have area xz. So there's two of those. All right. And the bottom of the box has area xy. There is no top, so there's only one of those. So plus xy, right? So this thing needs to be equal to 12, right? So this is the constraining function here. This is the constraining function. We're trying to maximize volume subject to this constraint on the area, okay? All right, so we need gradients. Gradient of f, let's see here. So that would be what? Yzi plus xyj. Oops, that's not right. Xzj plus yzk. Look at this right here now. Plus xyk, yeah. xyk, right? Okay, so there's the gradient of f. Is that what I got here? Yeah, good, all right. Gradient of g, let's see here. So let's see, this is a constant, so it's toast. This leaves a 2z, and then this leaves just a y, so you've got 2z plus yi, right? And then, let's see, my constant of y, so then you've got 2z here, and that's a constant, so it's gone, and that leaves an x, so plus x for j. And then what do you have? Z, you've got 2y plus 2x k, right? Everything look good there? Yeah, okay. So there are the gradients, right? So what we need is gradient of f equals lambda gradient of g for some lambda. Well, we certainly equate piece to piece here. So we have three separate equations going on, right? Because we're equating the I pieces to the I pieces here, and the j pieces to the j pieces, and the k pieces to the k pieces. So this leads to what? Let's see, so yz equals lambda times 2z plus y is one equation for the I components. For the j components, xz equals lambda times 2z, oops, that should look like a 2. Lambda equals 2z plus x, and then yk, xy, xy equals lambda times 2y plus 2x, right? Okay, so there are those equations that we have to satisfy. Looks good there. And don't forget, whenever we wind up here, the x, y, z's have to satisfy the constraining function too. So it has to satisfy 2yz plus 2xz plus xy equals 12. So there's a system of equations that our x, y, z's have to satisfy. Okay? 4 equations. Okay. So, what in the world do we do now? Well, again, so there really is not a general way to handle systems of equations. So sometimes you have to kind of do what you got to do to get through them, and it requires a little bit of ingenuity. So what you could do is you could equate all of these to lambda, set them all equal to each other, and then kind of play around with things and plug them eventually down here. But actually, what I want to do is the following. So where am I here? So we're starting down here. Okay, I'm actually going to make the left side of these look exactly the same, because if you notice, each one looks almost alike, except this is missing an x, and that's missing a y, and this is missing a z down here. So I'm going to make the left sides all equal, and then equate the right sides of what I get. Okay? So to do that, I'll multiply through by an x and an x on this top one here. So I'll get x, y, z equals lambda, let's see here, and that's 2xz plus xy. And then I'll get, for the second equation, I'll multiply through by a y over y here, right? And I'll get xyz equals lambda times 2yz plus xy. And the bottom equation, hit it with a z here and a z here. So I get xyz equals lambda, and then you get 2yz plus 2xz. Okay, right? Okay, so now all of those are equal to each other, right? So what am I going to do now? Okay, so now, so these are equal to each other. Now I'm going to look at how can I get these right sides to give me meaningful information. Well, these top two right-hand equations are almost the same. The only difference is there's a y here and an x here. So let's play with those for a minute. So let's take these top two and come over here. So we have lambda 2xz plus xy equals lambda 2yz plus xy, right? Well, certainly lambda's not 0. If lambda was 0, this would be dumb. So lambda's not 0, so we can divide by lambda and get out of there. And then we can subtract xy from both sides, so we wind up with 2xz equals 2yz, right, because the xy's are gone. And then you can divide by z, because if z was 0, this wouldn't be a rectangular box, but it can't have height 0, it wouldn't hold any volume, so that'd be dumb, right? So you can divide by z, you get 2x equals 2y, get x equals y, right? Yes, that's what I got. All right, good. So you have that. All right, we're getting somewhere. Okay? So now let's come, what am I doing now? Plugging it in somewhere, looking at the bottom two. Yeah, is that right? 2xy plus 2yz. Yeah, sure. So now I want to look at this equation and this equation down here. Yeah. So let's look at those a minute. So we have lambda 2yz plus xy equals lambda 2yz plus 2xz, right? And again, these are slightly different, but you know, there are two parts that are equivalent to each other. So again, we can divide by lambda. It's not 0. Get rid of that, right? So we get we can subtract xy. Well, actually, we can subtract 2yz from both sides. So if we do that, if we divide by lambda on both sides, and we subtract the 2yz from both sides, we get xy equals 2xz. What does that tell us? Well, x is not 0, yeah. Again, if x was 0, it wouldn't have a rectangular box. It would have it wouldn't have a length on one side, so that's not going to work. So we get y equals 2z. Okay. Aha. So yeah, here we're getting somewhere. Okay, good. So what have we got after all this? Is this what I wanted to say? Yeah, this is good. Okay. So we have x equals y equals 2z. All right. So we have all the variables in terms of each other. All right. And this is good because we haven't dealt at all with this last equation yet. We fooled with all these up here, gotten things out of this. We still have to satisfy this one down here. But now we can get them all in terms of one variable, all right, in terms of, say, z, right? So now, after this, let's see. Let's get rid of this stuff. So we have that. So now we're going to take this information and plug it in to this last constraining equation down here. So we started with 2yz plus 2xz plus xy equals 12. And let's get it all in terms of z here, right? So we have 2 times 2z times z plus 2 times 2z times z plus 2z times 2z equals 12, right? So I'm just plugging in 2z down the line for x or y, right? So what do you get? You get 4z squared plus 4z squared plus 4z squared equals 12. That means that what, 12z squared equals 12, z squared equals 1. Well, z is a height of a rectangular box. It can't be negative, so z must equal 1. Okay, well, this is great. So z is 1, so that means x is 2, and y is 2. All right? And those are the only, so these are the exclusive points to satisfy this. So 2, 2, 1 is the only point that satisfies all our requirements. All right, so after all that, we got 1 point out of there, which is good. It's nice, makes our second task easier. If we had more than 1 point, we have to plug them into f and see what was going on, but we don't. We only have one possible point for a max. So as a consequence, f of 2, 2, 1 equals 2 times 2 times 1, which is 4, and this is in meters, yeah, 4 cubic meters is the max volume. Whew, all right, so you can see that when you solve one of these, you've really put some effort into it, and so you should feel good when it's over. But there's the max volume. Okay, let's try a slightly easier one maybe. So let's get rid of this. Let's look this time at the geometry of what's going on now. It's easier to see in the 2D case. And let's go to blue to give ourselves some variety. So this time, let's find the max and min values of the function, what do I got here? 3x plus 4y, some linear function, right? On the circle x squared plus y squared equals 1. Okay? Okay, so your function is 3x plus 4y. Your g needs to equal 1, x squared plus y squared. All right? So let's do the gradients. All right? Gradient of f is, what, 3i plus 4j? That's pretty easy. All right? Gradient of g. Remember, I don't care if this is on the other side or not. It's just a constant. It's not going to matter, so you can leave it right here. Doesn't make a difference. So this is 2xi plus 2yj. Right, so there's your gradients. What am I doing now? Yeah. So then we got to do the old multiplier trick where we play, can we find a multiplier that makes this true? So we equate I and j parts again. This is much easier than last time because we don't have such horrible equations. We have 3 equals lambda 2x. And we have 4 equals lambda 2y. And we also have the constraint and x squared plus y squared equals 1, right? So we have those two equations there. And we have this. So I'm going to solve for x and y, then plug them in here and explicitly solve for lambda this time. So different ways of doing things. So let's see here. So I'll start here. So I'll solve for x. So x is equal to 3 over 2 lambda. Right? And again, lambda is not 0. It's not going to matter if we divide by it. And y is equal to, what, 2 over lambda? Is that right? Because 4 over 2 is 2. Yeah, that's right. So 2 over lambda. So if I plug them in down here, what do I get? I get 3 over 2 lambda squared plus 2 over lambda squared equals to 1. And let's see, do some work on that. what do you get? You get 9 over 4 lambda squared plus 4 over lambda squared equals 1. All right? Common denominator here is 4 lambda squared. So that leads us to 36 over, that's not right, no. It leads us to 9 over 4 lambda squared plus 16 over 4 lambda squared equals 1. Okay? Get rid of the denominator. You basically got 25 equals 4 lambda squared. Lambda squared is 25 fourths. All right? Take the square root of that, and lambda equals kind of like an x, doesn't it? Make my lambdas look a little better. So lambda equals, this should probably be an arrow, yeah. So lambda equals plus or minus 5/2. Right. Okay. So there's your lambda, right? I'm doing now here. Yeah, okay. So you plug it into your original equations for x and y, you can get x and y points. All right, so you got your lambda value. This time we actually solve for the explicit lambda, which is one way to do it. Have to do it that way every time. We didn't do it last time. You plug it in here. You get 3 over 2 times plus or minus 5/2 equals x, and you get 2 over plus or minus 5/2 equals y. So x is equal to plus or minus 3/5, and y is equal to, what, plus or minus 4/5? Yeah, okay, so there's your x and y's. This time you actually do have more than one point to check, right? Okay, so that's all done. So these are the possibilities. Possibilities for max min on the circle, right? So now let's plug into f, right? So you plug into f, and really, let's get rid of this stuff. You don't need to really plug in here to see what's going on. I mean, so your points are like 3/5, 4/5, negative 3/5, negative 4/5, 3/5, minus 4/5, and negative 3/5, positive 4/5. Well, I mean, which one? So you can plug them back into the equation and see which one maximizes, right? So let's see here. Is that right? Yeah, that's right. So you plug in either 3/5 or 4/5, negative 3/5, negative 4/5, right? And what do you get here? You get, oopsies, what am I doing? Yeah, I see what's going on here. Okay, yeah. So those are your possibilities. Plug into x. Yeah, okay. So both of these are positive coefficients. Okay, I see what's happening here. So both of these are positive coefficients. So when I plug in a positive number that are both positive coordinates, we should definitely get the largest possible max. And this, when they're both negative, should get the largest possible min, right? So if you check them out, you'll find this is confirmed. You plug in the point 3/5, 4/5, you get out what, 25/5, which is 5, right? So this is 3 times 3/5 plus 4 times 4/5, right? And if you plug in negative 3/5 and negative 4/5, you get negative 25/5, which is negative 5, which is 3 times negative 3/5 plus 4 times negative 4/5. And if you try either one of these points over here, where one's negative and one's not, well, the negative piece is going to push it negative, and the positive piece is going to push it positive. It's going to be somewhere less extreme than one of these. So these are the extreme values. So this is the max, 5, and this is the min, negative 5. So the max is 5, the min is negative 5. Okay? All right, so that's the algebra behind this. Let's look at the geometry for a minute here and see what's going on. So intuitively, we kind of knew it'd be these points that were going to work. Let's see why that's true. Let's draw a picture. So here's a coordinate axis. There's a unit circle, right? So there's x squared plus y squared equals 1. let's draw some lines. Let's draw the line 3x plus 4y, something like that, and maybe look something like that, and like that, and like that, and like that, right? So like this is the line, say, 3x plus 4y equals 5. This is the line 3x plus 4y equals, I don't know, 2.5. 3x plus 4y equals 0. 3x plus 4y equals negative 2.5. 3x plus 4y equals negative 5, right? So those are all level curves of f, right? Functions where f is equal to a constant, right? And so let's see here. Let me mark off these points. So notice that this is the point where it appears to be tangent there, and then you have a point similarly down here where it appears to be tangent. So there's 3/5, 4/5. There's negative 3/5, negative 4/5, right? Those are the points of tangency, and those are the level curves upon which they lie, right? And so where am I marking this here? So I don't want to put it right there, did I? So let's see here. So what's the gradient of f? Well, I erased it, but the gradient of f was 3i plus 4j, right? Well, that's a vector that points like that. So this is gradient of f, right? And then notice that's orthogonal to the level curve right there, right? And then down here, we see the exact same behavior, only it's negative, right? So this is negative gradient of f, and again, it's orthogonal to the level curve. And why is that true? Well, remember, the Lagrange multiplier was 5/2, right? Or plus or minus 5/2. So up here, you have the gradient of f is 5/2 times the gradient of g. And down here, well, this is negative direction because the gradient of f is negative 5/2 times the gradient of g, right? Right? So this is gradient of f is 5/2 times gradient of g. Down here, it's negative 5/2 times the gradient of g, right? At the points of tangency, right? And at the other point, let's see here. So, yeah, that looks right, yeah. So remember, these are tangents of level curves here, so everything's good there. And notice that as the lines go further from the origin, so as the lines move out that way and the lines move out that way, right, we're going to get bigger extreme values because the circle values are going to get larger, right? So clearly, you know, the points 3/5 and negative 4/5, well, that's, you know, down here somewhere. Well, it's not going to be an extreme value because it's on a line that is going to pass, you know, basically through the origin there. So as the lines move further from the origin, I should say the absolute value of f increases. Absolute value of f increases, right? And the extreme values get larger. Extreme values get larger. Okay, so this is what's going on with the geometry there. Okay. All right, how about, let's go to another problem here. So everything's good there, all right? So a couple different scenarios with how this could go. We'll look at one more thing here, which is two constraints. All right, we'll look at one more thing, which is two constraints. So two constraints. All right, and so now you're optimizing some function, so you want to optimize that function. And now you have two constraints subject to, say, some g of x, y, z equals k, and some h of x, y, z equals c. Okay? So you have the two constraints. All right? And so you are looking for extreme values on the curve of intersection big C between those level surfaces. So you're looking for the curve of intersection big C between the level surfaces G and H. Okay, so there's that. Let's look at a picture and some analysis here. So that's what you want for a two-constraint problem. Okay, so you have some point, x naught, y naught, z naught. Let's say it's an extreme value on C, value of f on C. Well, what's true about that point then? Well, we know that the gradient of x naught, y naught, z naught is orthogonal to C at that point, right? That's the same thing we'd had before, so gradient's orthogonal to each level curve, right? Okay. And what else? So G and H are both level surfaces, and we know that the gradient is orthogonal to a level surface at every point on there. So the gradient of G is orthogonal to C at that point, because it's a level surface. And the gradient of H is orthogonal to C at that point. Right? So you know that. So you know that gradient of F is orthogonal there, gradient of G is orthogonal there, gradient of H is orthogonal there. So let's draw a picture. So let's see here. And we'll let's use two different colors here. That'll probably work well. So we'll draw, so there's, okay, and then say we have, yeah, it looks right. Let's see here, and we'll put this looking like that. So we'll make C sort of coming out of there. And how does that look? Cruddy? A little bit. Here, let's put this a little further up there. All right. And yes, that looks better. Okay. So, and then let's finish off. Let's see here. So we want that to look like that. And our line of intersection is what? Where's black? So our line of intersection is like that line right there between those two level surfaces, right? So there's level surface H, level surface G. So we'll put H is up here, and this is the level surface G equals K, all right? And actually I wanted to put H on the other side here because I wanted to put something else right there. So that looks good. There you go. And then that's H equals C. Okay. So what you have, so let's see here. H is the red. So the gradient of H maybe looks like that. So that's gradient of H. Right? It's orthogonal to that level surface at every point. And the gradient of G, maybe it looks something like that. Right? And the gradient of F is also, so the black line, all kinds of colors going on here. The black line is the intersection curve, C. The gradient of F is also orthogonal there, so it's going to be coming out like that, gradient of F, right? And so look at what's happening here, right? We have a plane formed by the vectors, so the gradient of F of x naught, y naught, z naught, it's going to lie in the plane formed by gradient of G at x naught, y naught, z naught, and gradient of H at x naught, y naught, z naught, right? It's going to lie in that plane, correct? And so think about how vectors are added up, right? Gradient g plus gradient f would give you something that lies in gradient, or would give you something that lies in the plane. So therefore, gradient f is a sum of scalar multiples of gradient g and gradient h. So in here you're thinking vector addition, right? So like if I were to add some multiple of gradient h here, I would get over to gradient f, right? And it lies in this plane because they're all orthogonal at the same point. Okay, so what does that mean in the long run? Well, it means that the gradient of f is equal to lambda gradient g plus mu gradient h, right? It means that the gradient of f is equal to lambda gradient g plus mu gradient h, some sum of scalar multiples, where lambda and mu are Lagrange multipliers. Okay, let's do a problem here. Also, it's worth noting too that any max or min must satisfy not only this equation, but also g of x, y, z equals k, and h of x, y, z equals c, right? So you have to satisfy this equation and the underlying constraints. Okay, so let's do an example. Get rid of all this. All right, picture's gone. Okay, so let's maximize f of x, y, z equals x plus 2y plus 3z on the curve of intersection between two planes. The planes will be x minus y plus z equals 1. And actually between the plane and the cylinder, x squared plus y squared equals 1. Okay, so you want to maximize that function on the intersection between a plane and a cylinder, right? Well, this is a circular cylinder, so how does this look, sort of? So there's the cylinder, right? You have some plane chopping through it at some point, so boom, boom, like that, right? And then I guess this should actually probably be, let's see, so that looks good. We should lop off some part of this to make it look decent, right? And so what are they going to intersect in? Well, the plane's going to hack in here and make a circular cross-section, or actually an elliptical cross-section, so you're going to end up with an ellipse, right? You're going to end up with that elliptical cross-section being formed by the intersection of this plane and that cylinder, right? So we want to find the max on this ellipse, right? So that's the cross-section formed between this cylinder and that plane is an ellipse, right? It's not a circle because it's not a flat plane, it's an ellipse. Okay? Okay, so what are these things? Gradients, first of all. Gradient of f is I plus 2j plus 3k. All right? That's gradient of f. Gradient of g is I minus j plus k. Gradient of h is 2xi plus 2yj. Is that right? Everything look good there? Yeah? Okay. So we have gradient of f equals lambda gradient g plus mu gradient h. What does that give us? Well, we equate I parts in each one of these. So we have 1 equals lambda plus 2 mu x. All right. We have 2 equals negative lambda plus 2 mu y, and we have 3 equals lambda. All right, there's no k term down here. Well, and also we have the underlying constraints, x and x squared plus y squared equals 1, all right? Okay, well, we know that lambda is equal to 3. That's a big help. So let's get rid of this. So let's try to get an expression for x and y in terms of mu. So lambda equals to 3 implies what? That, what are we doing here? We're looking at this first expression here. Yes. So we have 1 equals 3 plus 2 mu x, plugging in 3 for lambda, right? That means negative 2 equals 2 mu x. So x is equal to negative mu. Is that right? Negative 1 over mu. Yeah, negative 1 over mu. Yes. Okay. And then we do the same thing for y. Lambda equals 3. Plug it in here, actually. So now we have 2 equals negative 3 plus 2 mu y. We have 5 equals 2 mu y. So y equals 5 over 2 mu. Okay, so we have that expression and that expression for x and y now, right? Okay, well, we have this constraint down here in terms of just x and y, so let's play around with that. See if we can't solve for mu. So we plug it in, so x squared plus y squared equals 1. Negative 1 over mu squared plus 5 halves, 5 over 2 mu squared equals 1. 1 over mu squared plus 25 over 4 mu squared equals 1. Get a common denominator. 4 over 4 mu squared plus 25 over 4 mu squared equals 1. This implies that 29 equals 4 mu squared, and mu squared is equal to 29 fourths. So mu, getting sloppy with my mu's down here. So mu is equal to plus or minus root 29 over 2. Okay? So we got values for x and y. We plug them in, solve for mu. There's 2 values of mu there, right? Okay? Are we almost done here? Yeah, we are. So get rid of that stuff. We now know the values of mu. Let's get values for x and y. Well, if you plug in plus or minus root 29 over 2 and divide by negative 1, you get x equals minus plus 2 over root 29. And I'm saying minus plus because when I plug in positive root 29 over 2, I get a negative 2 over root 29. When I plug in minus root 29 over 2, I get a positive root 2 over 29. So this is reversed from that. Okay? It's reversed. When I plug in plus or minus 29 over 2 here, I get, let's see, so the 2's are toast. So you get plus or minus 5 over root 29. And notice here the plus or minus is preserved because when I plug in positive here, I get positive here. When I plug in negative here, I get negative here. Here it was reversed. Here it's the same, right? Okay? So where am I now? The last constraint, x minus y plus z equals 1. So we're almost there. We have x and y, good. We need to get z values here. So you can certainly plug them in piece by piece if you want. That's fine. You don't have to, though. You get z equals 1 minus x plus y. And let's see, what does that lead to? So it leads to, what? X plus y, yeah, that's right. So in the case where remember, when mu was root 29 over 2, x was negative and y was positive. So x being negative means this will be a positive down here. So z is either 1 plus 2 over root 29 plus 5 over root 29. And when mu was a negative, x was a positive, y was a negative. So that's minus a positive plus a negative. So there's double negatives there. So it's minus that, minus that. So you can certainly do it one by one, or you can kind of be a little bit quick about it and do it this way, right? And so the bottom line is z is equal to plus or minus 7 over root 29, because There's positive 7 root 29. There's minus 7 root 7 over 29. And so if you plug all that in, I'm not going to do it on the board, but if you plug all those in, what you have is you have 4. So let's see, you have points that look like negative 2 over root 29, comma 5 over root 29, comma 7 over root 29. That's one possibility. The other possibility is you have 2 over root 29 minus 5 over root 29, and that leads to a minus 7 over root 29. These are your two possible choices here for f, right? So you plug these in here. What in the world was f originally? F was, where is it? X plus 2y plus 3z. Well, it certainly looks like this will be the max up here, and it ends up being that way. So let's see here. When you plug in negative 2 over root 29 plus 2 times 5 over root 29 plus 3 times 7 over root 29. What in the world do you get? You get negative 2 and 10 and 21, so 31, so 29 over root 29, something like that. That sounds decent. So there's your max value at that point, right? Did I miss something here? I did, yeah. So hold on, wait, go back. So this should actually be, I forgot the 1 down here. Forgot the darn 1. This should be 1 plus 7, 1 plus or minus 7 over root 29. Yeah, it looks better, yeah. Okay, so your points are actually not going to be that. They're going to be 1 plus 7 over root 29. Ha, glad I caught this. And then 1 minus 7 over root 29. That looks better. And then you plug 1 plus 7 over root 29 in there. And then you get not 20 over 29, but you get 3 plus 29 over root 29. And that's the max value. Okay, that's it for the section.